Hi, in this video we will discuss case study 4. This case study 4 is covering chapter 5 about the design of prismatic beams for bending. To answer this kind of problem, we need to list all of the known given in the question. We have the maximum allowable stress is equal to 160 megapascal. Then we have the dimension of the system. First, we need to draw the free body diagram of the system to find the reaction forces acting on the system. We have a reaction forces at point B and point D. For point B, we have a reaction forces at X direction and Y direction. But because there is no external forces on X direction, we can assume that the reaction forces at point B in X direction is equal to 0. Then we need to find the reaction forces in Y direction. We can use a sigma moment at point D equal to 0 to obtain the reaction forces at point B in Y direction is equal to 120 kilonewton. Then we can use a sigma moment at point B is equal to 0 to find the reaction forces at point D in Y direction. It is equal to 40 kilonewton. Then after obtaining the reaction forces acting on the system, we can create a partition. We have the first third partition for this beam. We have the point where it is just after the point A, and then the second partition is just before the point B or on the left part. We call it as VB1, and then we have the right part after reaching point B, or we can call it as VB2. And then we continue to the fourth partition and the fifth partition. We have a VC where it is just after reaching point C, after the distributed forces. And then the fifth partition is just before reaching point D. From the partition that has been created, we can calculate the V for each partition. The first one, we have VA is equal to 0, then VB1 is equal to minus 40 kilonewton, and VB2 is equal to 80 kilonewton. And then we go to the next partition. For the fourth partition, or VC, we will obtain minus 40 kilonewton. And then for VD, we can get minus 40 kilonewton. And then from the partition that has been created and we found the V for each partition, we can create the shear force diagram. We have VA equal to 0, VB1 is minus 40, VB2 is 80, VC is equal to minus 40, and VD is minus 40 kilonewton. So we can create the shear force diagram as shown in this figure. Then after creating the shear force diagram as shown here, we need to find the point P where it is intersecting the 0 point. We can use a congruence and similarity theories to obtain the distance from B to point P, and it will give us 1.6 meter. Then by calculating the areas below the graph, areas here, 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 and here, we can obtain the moment in the system. From A to B, we will obtain a minus 16 kilonewton meter as the area. We can use a triangle formula to calculate the area below the graph. Then from P to P is equal to 64 kilonewton meter. From P to C is equal to minus 16 kilonewton meter. And from C to D is equal to minus 32 kilonewton meter. After obtaining the area below the graph from the SFD, we can create the bending moment diagram based on the shear force diagram. For the bending moment itself, for MAB, we have a minus 60 kilonewton meter as the area below the graph from A to B. So it will become the value of moment in this graph. This is point A to B. Then from P to P, it's 64 kilonewton meter. So for the peak of this curve, we will have a 64 kilonewton meter minus by 16. So we will obtain a 48 kilonewton meter. Then we go to the next partition. From P to C, we have a minus 16 kilonewton meter as well. So by adding up from the previous result, it will give us a 32 kilonewton meter. Then from C to D is equal to 32 kilonewton meter. So at point D, the result will be 0. 32 kilonewton meter minus by 32 kilonewton meter. So from this bending moment diagram, we can conclude that the maximum moment occur is 48 kilonewton meter. Then after we know that the maximum value of moment is equal to 48 kilonewton meter and the maximum elbow stress is 160 megapascal. So we need to design the beam that having a minimum S is equal to moment over the elbow stress. By substituting the value, we will obtain that the minimum S is equal to 0.3 times 10 to minus 10 power minus 3 meter cube, or it is equal to 300 times 10 cube millimeter cube. From the table in appendix, in axis XX, we need to find the SX that more than 300 times 10 cube millimeter cube, but the lightest one. So the SX that we can use is 416, 308, and the last one is 342 times 10 cube millimeter cube. If we look closer into the option, we can see the weight of the beam. For the 416, we will have a 32.7 kilogram per meter. And then for a 308, we will have a 28.4 And for the last option, 342 for the Sx is equal to 35.9 kilogram per meter. So if we consider the lightest beam that we can use, we choose the W 250 times 28.4. So the lightest beam and strong enough to hold the load of the beam, we can choose the W 250 times 28.4 kilogram per meter.